we will study about Mosfet, that is metal oxide semiconductor field effect transistor. Okay, so Mosfet, it is generally used in almost all CMOS digital integrated circuits. Okay, so MOS, it is used in almost all digital integrated circuits. The main advantage of MOSFET as compared to BJT is that here the fabrication process is very simple as compared to BJT, and also MOS transistor occupies a very smaller area, and the power dissipation by using MOSFET, it is also very small as compared to bipolar junction transistor. That is why MOSFET is generally used in almost all CMOS digital integrated circuits, in almost all LSI and VLSI circuits. Okay, so nowadays we are using MOSFET instead of BJT for in LSI and VLSI circuits because it occupies less area, its fabrication process is very simple as compared to BJT, and also the power dissipation by MOSFET, it is very small as compared to the BJT. Because of this advantages, we are generally using MOSFET as a switching device in LSI and VLSI circuits. Now we will study about MOSFET. MOSFET, it is a 3-layer device. This is a 3-layer device. This is a 3-layer device and 4 terminal. Okay, it is a 3-layer device. 3 layers are, that is MOS, it is metal oxide semiconductor. These are the 3 layers. It is MOSFET. It is metal oxide semiconductor field effect transistor. Okay, so it is a 3-layer. The first layer is metal layer, second layer is oxide layer, and the third layer is semiconductor. Okay, so we can draw a MOSFET like this. This is metal layer, this is oxide layer, and oxide it is SiO2, metal generally aluminum or polysilicon. Okay, this is gate terminal, this is source terminal, this is drain terminal, and this is substrate or body terminal. So a MOSFET, it is a 3-layer device. The 3 layers are metal, oxide and semiconductor. Metal, generally aluminum or polysilicon is used, oxide SiO2 is used, and in substrate either in the silicon used may be p-type or n-type depending upon the which type of MOSFET we are using. Okay, and so it is a 3-layer and 4 terminal. Four terminals are source, gate, drain and body or substrate. S stands for source, G stands for gate, D stands for drain and B stands for body or substrate. Okay, so these are the 4 terminals and 3 layer. Okay, so a MOSFET can be of 2 types. First one is enhancement type, and the second one is depletion type. So 2 types of MOSFET we are seeing. First one is enhancement type and the second one is depletion type. Enhancement type, channel has to be created. How channel can be created? Channel has to be created by applying voltage at the gate terminal. And in case of depletion type, channel is already created even at Vg is equal to 0 volt. Okay, so here if Vgs, if it is also equal to 0 volt, then also channel is created, and here channel has to be created by applying the voltage at the gate terminal. Okay, so this is the main difference between enhancement type and depletion type. Again, enhancement type may be N channel MOSFET or P channel MOSFET. So we will study about enhancement type. Okay, so enhancement type may be either N channel MOSFET or P channel MOSFET. Okay, so this is the diagram of N channel enhancement type MOSFET. So in case of N channel enhancement type MOSFET, the substrate or the semiconductor, it is of p type silicon. P-type silicon is used as a substrate. Okay, and the terminals are source, gate, drain, and body or substrate. Similarly, in case of P channel, in case of N channel MOSFET, that is N channel enhancement type MOSFET, the substrate used is P-type semiconductor, and channel is N-type. Whereas in case of P channel MOSFET, the substrate used is N-type. The substrate used will be N-type in case of P channel, and the channel will be P-type. Okay, so what is this channel? We will study later on. This is channel length and channel width is W, and this is TOX. So this is the representation of N-channel enhancement type MOSFET. Here we are seeing that this L is the channel length and W is the channel width, and TOX is the thickness of the oxide. This TOX, this is TOX from here. This is TOX. This is TOX. Okay. So L is channel length, W is channel width, and TOX, it is thickness of the oxide. Thickness of the oxide means thickness of SiO2 layer in between metal and the substrate. Okay. So all these L, W and TOX, these play an important role in determining the electrical characteristics of Mosfet. Okay. So we are seeing that this metal layer, this is metal layer and this is substrate. In between metal layer and in between substrate, an oxide layer exists in case of Mosfet. So it behaves, this complete structure behaves as a capacitor also. It behaves as a capacitor. Here the two plates, outer plate and inner plate are metal and the substrate, and in between these two plates oxide behaves as insulator, so it acts as a capacitor also. Then we will study about Mos structure under external bias. Mos structure under external bias. Okay. So suppose this is Mos structure, this is metal layer, this is oxide layer, and this is substrate. Suppose this is for N Mosfet. N Mosfet means N channel enhancement type Mosfet. So suppose this is gate terminal and this is metal, this is oxide, and this is P type substrate. Okay. So depending on the voltage that is applied to the gate terminal, three types of regions are created. First region is accumulation region. Second one is depletion region, and the third one is inversion region. So this metal oxide semiconductor effect transistor. So we have studied this is metal oxide semiconductor, and why it has got the name of field effect transistor. See, the conduction in Mosfet takes place by creating electric field due to the application of external voltage at the gate terminal. That is why it is known as field effect transistor. Due to the application of external electric field, conduction takes place in field effect transistor in this device. That is why it is known as metal oxide semiconductor. This is metal oxide semiconductor. And why it is known as field effect transistor? Field effect transistor because by the creation of electric field. How electric field is generated? Electric field is generated due to the application of external voltage at the gate terminal. So by the creation of electric field, conduction can take place in this device. That is why it is known as FET device. So it is Mosfet. Now, depending upon the application of voltage at the gate terminal, three types of regions are created. First region is accumulation region, second one is depletion region, and the third one is inversion region. So first is how accumulation region is created in case of MOS transistor, that is N-channel MOSFET. You can see if at the gate terminal, that is VG, if it is less than 0 volt, and always remember the four terminals are source, drain, gate and body or substrate. So all the terminal voltages are measured with respect to the source terminal. So it is VDS, VGS and VB with respect to source. This is drain to source voltage, gate to source voltage, body to source voltage. Okay. So in case of MOSFET, we are always measuring the terminal voltage with respect to the source voltage. That is why it is VDS, VGS and VBS. So if VG or if VGS, if it is negative, then what will happen? Okay. See, in case of N-channel MOSFET, the substrate is P-type substrate or P-type silicon. Here P-type silicon is used. P-type silicon is used. So in case of P-type silicon, the majority carriers are holes. The majority carriers are holes, and you can see here it is grounded. We are grounding this substrate terminal. Okay. Now what will happen if VGS is less than 0? If we are applying a negative gate voltage to the gate terminal, then what will happen? Then here in case of P-type silicon, the majority carriers are holes. So holes will be attracted. Holes will be attracted and it will be accumulated. It will be accumulated in the oxide substrate interface layer. This is oxide substrate interface layer. Okay. So here we can see the concentration. Here the concentration of holes is more than the equilibrium concentration of carriers. Okay. Because of negative gate to source voltage, the holes will be attracted. Holes will be attracted and it will be deposited on the oxide substrate interface layer. This is the oxide surface interface layer. So it is the accumulation of holes or accumulation of carriers. So this is accumulation of holes or accumulation of carriers, and we can see that the concentration of holes here it is more than the concentration of carriers, equilibrium concentration of carriers in other places. That is why it is known as accumulation of carriers on the oxide substrate interface layer, and this region is known as accumulation region. So accumulation region can be created. So we can say that accumulation region can be created when VGS is less than 0 volt in case of N-channel MOSFET. Okay. So here the accumulation of carriers, that is the accumulation of holes, take place in the oxide substrate interface layer. Okay. So this is all about accumulation region. Then we will see about depletion region. Second region is depletion region. Here in depletion region, if VGS is greater than 0 volt but it is very small, if VGS is greater than 0 volt and its magnitude is very small, means less than the threshold voltage of this device. So you can write less than VT naught, that is the threshold voltage of the device. So what will happen when we will apply a positive gate voltage? You can see this is p-type silicon. Okay. So if a small positive gate voltage is applied at the gate terminal, then what will happen? Because of the application of a small positive gate voltage, the holes will be repelled. The holes will be repelled towards the substrate and its direction will be downward, and the direction of electric field, again it will be the direction of electric field, it is downward. So leaving behind negative fixed acceptor ions. This is negative fixed acceptor ions, which are immovable, that is, these are not movable, these are fixed acceptor ions. Okay. So how these are created? These are created by the application of gate voltage, that is a very small gate voltage less than the threshold voltage of this device. Then what will happen? It will, because of the application of gate voltage, that is positive small gate voltage, the direction of the electric field, it will be downward. Because of this, holes will move downward, leaving behind fixed acceptor ions. Okay. So this is the creation of depletion region. So depletion region is created this region is created near the oxide substrate interface layer, and in this region, that is in this depletion region, no any free carriers exist. So in depletion region also conduction does not take place. Okay. Then we will see third type of region, that is inversion region. Now we will see about how inversion region is created. If we are applying gate voltage greater than 0 volt, means, and it large magnitude. If we are applying a gate voltage whose magnitude is larger than the threshold voltage of this device, then the region that is created is inversion type. Okay. See what happens if we are applying a voltage greater than VT0 of this device. What will happen? You can see here, in case of p-type silicon, the magnetic carriers are electrons. The magnetic carriers are electrons. So because of the application of a large gate voltage, its magnitude is large, means greater than the threshold voltage of this device, then it will attract the magnetic carriers, and the magnetic carriers will be accumulated here in the thin region. These are the electrons. And the electrons will be attracted towards the oxide substrate interface layer because of the application of gate voltage greater than the threshold voltage of this device. So because of this, there is inversion of channel, or channel is created. See, before this, the complete structure, the complete layer, it is of p-type silicon. Now, by the application of VGS greater than VT0, means if VGS is greater than the threshold voltage of the device, then what happens? Earlier it was p-type. Now the channel it is created and it is inverted. It is inverted, means it has now become n-type. That is n-type channel. And because of the creation of this channel, conduction takes place in case of MOS transistor. Okay, so in this way channel is created. So channel is created due to inversion region. So inversion region is created how? When VGS is greater than VT naught of the device. That is, when VGS is greater than the threshold voltage of the device, then only channel is created. So once a channel is created in case of enhancement type MOSFET, then conduction can take place between the source and the drain terminal of the device. Okay, so this is the basics of MOS transistor. Then we will study about this is an MOSFET. This is VGS. Suppose if it is grounded, this is VDS, and also suppose this is again grounded. Okay. This is the symbol for, this is the structure of n-channel MOSFET. In n-channel MOSFET, this is source terminal, this is drain terminal, this is gate terminal, and this is substrate or body terminal. Okay. Now the drain current, that is ID, it is a function of VDS, VBS and VGS. So ID, it is a function of VGS, VDS and VBS. Okay. The drain current, this is a function of VGS, VDS and VBS. VGS stands for gate to source voltage, VDS stands for drain to source voltage, and VBS stands for body to source voltage. Okay. Now, if we are connecting body to ground and again drain terminal to ground, then we are seeing the effect of ID by the application of VGS only. Then how we can relate this? See, if VGS is less than 0 volt, then no any channel is created, so ID it is equal to 0. Okay, so then if VGS is greater than or equal to VT naught, then only channel is created. Channel is created. Okay. So in order to create the channel, we have to give external voltage at the gate terminal in such a manner that it should be greater than or equal to the threshold voltage of this device, VT naught. VT naught is the threshold voltage of this device. Okay, so VGS has to be more than or equal to VT naught in order to create the channel. So after creation of channel, suppose channel is created like this. This is say n channel. This is N channel. So channel is created by the application of voltage at the gate terminal, and that voltage should be greater than or equal to the threshold voltage of the device. So channel is created, that is N channel is created. So it is known as N channel Mosfet. So channel is N type. Now once channel is created, so how ID, that is the drain current, flows between the source and the drain terminal. Okay, so then we have to apply, we have to give some drain voltage, that is VDS. We have to give some drain voltage, external voltage we have to give at the drain terminal. Okay, so if VGS is greater than or equal to VT naught, then channel is created. We know channel is created. After the creation of channel, if we are applying some external voltage at the drain terminal, then this creates a potential difference between the drain terminal and the source terminal. Okay, because of this potential difference, current can flow between the source and the drain terminal. Okay, so we can see if VDS, if it is equal to 0 volt, means if the potential difference between the drain and the source terminal is equal to 0, means both are at the same potential. If suppose if it is at ground potential and if it is at ground potential, suppose if it is at ground potential, then what will happen? Then in that case ID it is equal to 0. Okay, so this is in cutoff mode. Okay, if both are at the same potential, so VDS it is equal to 0, then in that case ID, there will be no any drain current between the source and the drain terminal. Okay, so ID here it is equal to 0 in this case. Now how current can flow between the source and the drain terminal? Then we have to give some potential at the drain terminal. So suppose VDS we are giving some positive value. Okay, now second case is if VGS is greater than or equal to VT naught, okay, that is more than the threshold voltage of this device, and if VDS is positive but small value, then what will happen? Then ID current will flow between the source and the drain terminal. Okay, so now in this case ID current it is linear proportional to VDS. So under this case, this is also known as linear mode of operation. So in linear mode of operation, VGS should be greater than VT0. This condition is required for the creation of the channel between the source and the drain terminal, and how current can flow. So this is determined by the application of external voltage at the drain terminal. So if VDS is small but positive, its value is positive, then there will be a drain current flow between the source and the drain terminal, and the drain current is proportional to VDS, and this operation is also known as linear mode of operation. Okay, then we will see third case. This is N channel, and if we are increasing VDS, what will happen? If VDS is increased further, then what will happen? You can see here. This is N plus, this is N plus, this is P-type silicon, and it is connected to ground, and it is VDS. If you are increasing this VDS, and this is VGS, and it is connected to ground. This is body. Now what will happen? If we are increasing this VDS, then the channel depth towards the drain terminal, it starts decreasing. See, earlier channel is like this. Now if VDS is increased, then this depth towards the drain, this is towards the source, and this is channel region. This is channel. This is N-type channel because this is N Mosfet. This is N Mosfet and N-type channel. And if we are increasing the drain voltage, then what will happen? The channel depth towards the drain, it starts decreasing. And again, if we are increasing this drain voltage, then what will happen? At certain time, it will be like this. So the depth towards the channel depth towards the drain terminal, it vanishes. By application of VDS, it is equal to VD as saturation. VDS saturation. Okay, so if VDS is equal to VDS saturation, then what will happen? This depth, the channel depth towards the drain region, it vanishes, and this is known as pinch off point. And this condition is known as pinch off condition. So pinch off condition occurs in saturation region, and this is in saturation mode. So in saturation mode, pinch off condition occurs, and this pinch off point, again this pinch off point it starts moving towards the source terminal by increasing this VDS more than VDS sat. So if VDS, if it is more than VDS sat, then what will happen? This pinch off point, it will move towards at this point, say this point. This is pinch off point. Earlier the channel length was this. Now the effective channel length, this is L effective. So in case of saturation mode, the effective channel length decreases because of this pinch off condition. If VDS is more than VD sat, then this pinch off point, it starts moving towards the source terminal. Okay, and we can see if in linear region like this, this is depletion region. Again, the depletion region, this is the depletion region. The depth of the depletion region at the drain terminal, its depth increases by the application of VDS by increasing VDS. So if we are further increasing VDS, then this depletion depth toward at the drain terminal, it starts increasing. Earlier it was almost equal, but if we are increasing this VDS, then this depletion depth it starts increasing. So again we can see this picture. This is depletion region. This is in saturation mode. VGS, and this is VDS more than VDS saturation. Then what will happen? The channel region, it is like this. This is channel. So this is effective channel length, L effective, and physical channel length, this is L. Okay. So L effective, it is equal to L minus delta L. This is delta L. This is delta L, and this is L effective of the channel. So in case of saturation mode, effective length of the channel is less than the physical length of the channel by an amount del L. We have seen in case of N-channel Mosfet, if VGS is less than 0 volt, then no any channel is created. Again, if VGS is greater than or equal to VT naught, then channel is created. Okay. So after creation of channel, then only ID current can flow. So now if VDS it is equal to 0 volt, then ID it is equal to 0. If VDS is equal to small positive value, then ID it is in linear region, and if VDS is more than or equal to VDS saturation, then ID it will be in saturation region. Okay, small means it is less than VDS saturation. Okay, so ID current, that is the ID current, it will be linear drain current, and here ID will be saturation drain current. Okay, so we can see that this is the circuit symbol for N-channel Mosfet, and this is the circuit symbol for P-channel Mosfet. Okay, so this is the circuit symbol for N-channel enhancement type Mosfet. Okay. Similarly, this is the simplified circuit level symbol for N-channel Mosfet. Here it is gate, drain, source, and body terminal it is missing. Okay, and this is also the simplified symbol for N-channel Mosfet. Similarly, for P-channel enhancement type, this is for enhancement type. Similarly, all these symbols are for enhancement type P-channel Mosfet. 4 terminal circuit level representation. The 4 terminals are gate, source, drain, and body. Okay, and these two are simplified version symbol of enhancement type P-channel Mosfet. Okay, so this we can see. Then the main difference between enhancement type and depletion type is that in case of enhancement type, channel has to be created by the application of voltage at the gate terminal. So in case of this is n channel MOSFET. In case of n channel MOSFET, if VGS, that is if we are applying the voltage at the gate terminal such that its voltage should be greater than or equal to the threshold voltage of the device, then only a channel is created. So before this means if VGS, if it is equal to 0 volt, then channel is not created. So current will not flow between the and source terminal. Okay, in case of enhancement type. But in case of depletion type, what will happen? In case of depletion type, a channel is already created. This is the symbol, circuit level symbol for n channel MOSFET. Channel is created by thick line. This channel is created by thick line. Okay. So in case of depletion type MOSFET, a channel is already created. Okay. So even if VGS, it is equal to 0 volt, then also channel is already created. Okay. In case of depletion type. So this is the main difference between enhancement type and depletion type. Now we will study the current voltage relationship in MOSFET. Okay. That is drain current versus drain voltage VDS for different values of VGS. So it will be like this. It will be like this. Suppose this is for VGS1, this is VGS2, and say this is VGS3. Okay. Now this is dotted line. This is dotted line, and similarly this is dotted line. So this is the graph when lambda is not equal to 0, and this is when lambda is equal to 0. Similarly, this is when lambda is not equal to 0, and this is when lambda is equal to 0. And what is this lambda? Lambda is channel length modulation coefficient, and this channel length modulation coefficient, it occurs only in saturation mode. Okay, and you can see this is linear region and this is saturation region. Okay, so in linear region ID, in linear region you can see in linear region of operation ID is directly proportional to VDS, that is it is linearly proportional to VDS in linear region. So this is, we can see this is directly proportional, almost linearly proportional to VDS. In case of saturation region, we can see ID is not directly proportional to VDS. It is like this. If here it is lambda, it is not equal to 0. In case of saturation mode, lambda, if it is not equal to 0, then we can see that it is somewhat elevated. And here, if we are not considering, if we are neglecting the channel length modulation coefficient or channel length modulation effect, if we are neglecting it, then the graph will look like this. And if we are considering channel length modulation effect, then the graph will look like this dotted plot. This dotted plot shows the graph between ID versus VDS for different values of VGS when channel length modulation effect is considered. Okay, so this is the current voltage relationship. Current means drain current and drain voltage relationship in Mosfet. Okay, now we can see that the ID, it is the drain current. So drain current, it will always be equal to 0 when VDS is less than 0 volt. This is in case of N Mosfet. This is in case of N channel Mosfet. So in case of N Mosfet, if VGS is less than 0 volt, what does this mean? This means that no any channel is created. So if no any channel is created, so ID, then ID it is always equal to 0. Okay. Now in linear mode, the expression for ID linear, it is equal to mu n cox by 2 into W by L into 2 VGS minus VT naught into VDS minus VDS square. This is in case of linear region. Okay, when VGS is greater than or equal to VT naught. So this is the condition for creation of channel. So once channel is created, then we have to apply VDS. So VDS should be less than VGS minus VT naught for operation of the N Mosfet in linear region. So in case of linear region, the ID, that is the drain current, it is equal to this expression. This is the linear drain current, and the condition for linear drain current, it is like this. This is for the creation of channel, and this is the condition for linear region. Okay. So for linear drain current, this is the expression. Then we will see about saturation current, that is ID sat. ID sat, it is equal to mu n Cox by 2 into W by L dash into VGS minus VT naught square. Okay. So what is this L dash? L dash is, this is in saturation mode. In saturation mode. So in saturation mode, effective channel length is always less than the physical channel length by delta L. Okay. So 1 minus delta L by L, it is approximately equal to 1 minus lambda VDS. What is this lambda? Lambda is channel length modulation coefficient. Okay. So it is equal to mu n Cox by 2 into W by L into VGS minus VT naught square into 1 plus lambda VDS. So because of this lambda expression for lambda, we have seen the dotted plot in suppose this is ID versus VDS, like this. This is when we are considering lambda. If we are not considering, lambda is equal to 0, lambda is not equal to 0. So if lambda is equal to 0, then the expression will be only this much. Expression will be this much. So this when lambda is equal to 0, this is the graph when lambda is not equal to 0. Okay. So the expression for drain current in linear region, in saturation region, and in cutoff it is equal to ID, it is equal to 0 in cutoff mode. Okay. So this is all about N channel Mosfet, the expression for drain current. Okay. We will see what is this lambda. This is due to this effect. This effect is known as channel length. This is channel length modulation. Due to channel length modulation occurs in saturation mode. So in saturation mode, because of this channel length modulation effect, the effective channel length, it decreases. because the pinch off point it moves towards the source terminal. With if VDS is more than VDSat, then what will happen? The effective channel length it decreases. It decreases because of this channel length modulation, and this effect is known as channel length modulation. Because of this, the pinch off point it moves towards the source terminal, and the effective channel length it decreases, and this phenomenon is known as channel length modulation effect. Okay, so because of channel length modulation effect, we have seen the expression here. This is channel length modulation coefficient lambda. Okay, and here what is this mu n? Mu n is the mobility of the electron. COX, what is COX? COX is gate oxide capacitance per unit area. W is channel width. L is channel length. VGS is gate to source voltage. VT naught is, what is VT naught? VT naught is the threshold voltage. Threshold voltage when the body is connected to ground. Okay, and similarly VDS is drain to source voltage. Here all the terminals are same, and here what is L dash? L dash is the effective channel length, and L dash is always less than the physical channel length. Okay. Then we will see about substrate effect. Substrate effect it occurs. How it occurs? When VBS. In all the cases, we are assuming VBS is equal to 0. Now, if VBS is not equal to 0 volt, that is, if we are giving some external voltage to the body terminal, then there will be variation in the threshold voltage of the device. And VT, now it is the VT when this is the threshold voltage. Threshold voltage when VBS is not equal to 0 volt. Okay, and VT naught, it is the threshold voltage. It is the threshold voltage when VBS it is equal to 0 volt. Okay, so this is the difference between VT and VT naught due to substrate bias effect. When the substrate is biased by some external voltage, it will vary. Because of the substrate biasing, there will be variation in the threshold voltage of the device, and it is known as substrate bias effect. So it will affect the expression for drain current in linear mode, in saturation mode, because in that case VT naught it will be replaced with VT, because VT is the threshold voltage of the device when VBS, if it is given some external voltage is given to the substrate terminal. Okay, so this is about substrate bias effect. This is substrate bias effect. Okay.